Welcome to the lecture for research methods. We'll be talking about hypothesis testing, which we'll be talking both about how to design hypotheses appropriately and then the logic behind hypothesis testing as it's currently used in behavioral science. So starting off, we should talk about probably what is a hypothesis. A lot of different definitions. Just one simple definition would be it's some statement about a relationship between or among variables. Something about some way you think the world is. And so when we talk about this relationship among variables, it's probably good for some of us anyway to have a quick reminder about, well, what are variables? Well, it's really anything that can take on more than one value. So depression can be a variable, level of aggression, gender is a variable, can be male or female or intersex. Um, time is a variable. How much hope somebody has is a variable. So really almost anything you can think of, if it can take on more than one value, it's a variable. And if you think, well, okay, there's some relation between this variable and this other variable, or this set of variables, then you have probably a hypothesis. Well, what kind of relationships are we talking about between these variables? Well, as you've read in Kasdan already, um, you may be talking about just a relationship between variables. It's referred to as a correlation. So that means the variable is related in some systematic way. And all that tells you is if I can measure one variable, then I'll know something about the level of the other variable. For example, if I think that maybe TV violence and being aggressive are correlated, that means they're related, but it may not be clear that one precedes the other. But I mean, okay, people that watch a lot of violent TV are pretty aggressive. The people that are pretty aggressive watch a lot of violent TV, but I don't know which one came first or if one causes the other. All I know is I think they're related. Um, if we go a step further, we'll look at risk factors. A risk factor is a correlation, right? So it's a type of relationship that's a correlation. So a systematic relationship where one variable is thought to precede the other one. So you're not necessarily causal relationships. I'm not quite there yet. So um, the correlation between ashtrays and cancer. If you have a lot of ashtrays in your house, then I know that you're probably at risk for having cancer. You know, and ashtrays are there probably before your cancer is there. So having the ashtrays becomes a risk factor, identifying things. Okay, you may have cancer in the future. Now, once we've established a causal relationship, now we talk about kind of cause and effect. This is when one variable changes, it causes changes in the other variable. So if you want to look at the relationship between smoking and cancer, there's a cause-effect relationship. So obviously, you know, ashtrays don't cause cancer, but smoking does. And we can look at not smoking compared to smoking. So changing from across levels of that variable causes changes in the other variable, from not having cancer to having cancer. So there's a simple causal relationship. Okay, so where do these hypotheses come from? Well, we've already talked about this when we talked about how to come up with research ideas. Just kind of sum up in general, hypotheses are derived from either theories or observations or some combination of those two things. Okay. So before we talk about hypothesis testing and some logic behind that, let's talk a little bit about hypothesis design, how to make good hypotheses. In your reading in Kasdan, you read about hypothesis validity, which is the extent to which the results of research accurately reflect theoretical predictions they were designed to test. So it's whenever you have a hypothesis that has good, strong hypothesis validity, and you test it and you get the results, it's meaningful and it relates logically to what you were hoping to test. A couple of points about how to increase your hypothesis validity. One, be specific. You know, don't make a hypothesis that just looks at the relationship between variables. Oh, I wonder if my hypothesis is that there's some relationship between x and y. You know, make some hypothesis about the direction. So when x changes, what happens to y? So if x is at high levels, y will be at high levels. Or if x is high, then y will be low. You know, make a specific prediction. Gives you more hypothesis validity, a clear picture of what you're doing. If you can, compare competing theories. Because as I've talked about multiple times, this is how science moves forward. Now, if your expected outcome would support one theory, but not another, now we've got a better idea of which theory has more support without needing to conduct as many studies. So kind of theories head to head, if you have a hypothesis that can do that, then you've got strong hypothesis validity. Another thing, limit the number of variables examined. This is for both statistical and logical reasons. Statistically speaking, the more variables you're looking at, the harder it is to find statistical significance. It relates to power, which we'll get into later. But also, the more variables you have, the more difficult it can be to interpret those relationships among multiple variables, especially if they don't all go exactly the way you expect them to go. And if you can't make sense of your results, then it's harder for you to really have a contribution to science. So better to kind of go after small bites instead of trying to do one ginormous study that considers all the possible things. Take on each aspect one study at a time and build one on the other. In that way, you're going to move forward with surer footing. And if you try to do too much at once, then you're going to slip and stumble and be left in a muddle. And then the last thing is be sure and use an appropriate statistical approach for your hypothesis. There needs to be a match between how your hypothesis is phrased and what statistical tests you choose. You don't ask a kind of a question hypothesis about group differences and then try to answer it with a series of correlations. And we'll talk more about this later when we talk about analyzing results and data analysis, which kind of know for now that those things need to match up. So keep that kind of in the back of your head. Other things about designing a hypothesis, we've talked before, again, about it's important for hypotheses to be logical, testable, falsifiable, and positive. In terms of being logical, think about kind of this formal statement of hypothesis. If A, then B, which is a conditional statement. Now basically you're saying if the variables you're looking at are related in some way based on theory observation, then you will see a particular pattern of results in a particular setting. So the first part, the if, is kind of the relationship you expect to happen, and the then is what you'd see in a study. Okay, an example maybe that help clarify. If you believe that playing violent video games causes violent behavior, so your statement would be if A, playing violent video games causes violent behavior, then B, people who play violent video games will exhibit more violent behavior than people who play non-violent video games. Okay. So again, that first part A is just the relationship, and then the B is some sort of observable, testable outcome you'd see if that first part were true. And one way to kind of examine the logic of your hypothesis is to look at the contrapositive of the conditional, and that's the if not B, then not A, because this is a valid inference of the conditional. So if you set it up correctly, where if A then B, then it's true that if not B, then not A. Some other variations not so valid, but this one is valid. It's kind of a good way to test. So for the hypothesis, the example I just gave you, that would be, so if B, if people who play violent video games do not exhibit more violent behavior than people who play non-violent video games, then A, playing violent video games does not cause violent behavior. Okay. Kind of an illogical hypothesis, just kind of give an example of that, would be if A, playing violent video games causes violent behavior, then B, violent criminals will like violent video games more than non-violent criminals. So in this case, the B doesn't necessarily follow logically from the A. And it sounds kind of like it might, but if you look at the contrapositive, it's more clear that it doesn't. So if we look at that, it would be if violent criminals don't like violent video games more than non-violent criminals, then playing violent video games doesn't cause violent behavior. Then, that just doesn't make sense. So even if violent people didn't like violent video games more than other people, this wouldn't disconfirm that games cause violent behavior. So liking them and the cause effect, it's clear that those aren't so strongly connected logically. So you can always look at, like I said, the contrapositive to double check your logic there. So if we look at just briefly the other ifs, so the other variations of this, if B, then A. So this would be kind of saying, okay, well, so if I find the pattern of results I'm looking for, then yes, my theory is true. And no, that would not be correct. That would be affirming the consequent, which is a logical error. If B, then maybe A. It certainly doesn't disconfirm A. It supports A, but it doesn't prove A, because that's not how the logic works of if A, then B. Um, Similarly, if not A, then not B isn't a valid inference. That's called denying the antecedent. So even if your theory is wrong, um, your observations might be what you would expect based on that theory, if that makes sense. So again, the only kind of inference you can make from if A then B is that first one. If not B, then not A. Okay. So only disconfirming a hypothesis that's logically based on a theory disconfirms the theory. But just because finding support for a theory doesn't prove that theory. Um, okay, so we've talked about kind of the importance of being logical and kind of what that logic looks like. In terms of being testable, think for a minute, well, which part of the statement is subject to testing or to observation? Was it the A or the B? Obviously, it's the B. The B is the observable pattern that you expect if some theoretical relationship was true. If you use the if-then format, you'll generally not have problems with testability. You'll see them if you do. Just as long as your then statement, the B part, is something observable, you'll be fine. Example of something that's not fine. Here's a if-then. If marital satisfaction is related to spiritual development, then couples who have more grace will be more satisfied with relationships than couples with less grace. There's nothing wrong with the if part of this, so the theory might be right, but the then part isn't really observable because you can't. We don't have any ways to measure grace per se, unless something comes up with a grace scale. Then it would then become testable, and it would be fine. Related to testability, we talked before about falsifiability. So it must be possible for the then portion, the B portion, to be shown to be false. So the example again I used before was if people can heal themselves by concentrating on certain images, then people who concentrate hard enough will heal their own wounds. Again, that's not falsifiable the way I've worded it. Then people who concentrate hard enough will heal their own wounds. Because if people don't heal their own wounds, then all I have to say is, well, they didn't concentrate hard enough. So it's not falsifiable as stated. And you notice that there's no comparison group there. And whenever you're talking about a cause-effect relationship, your hypotheses would probably need to talk about at least two groups to be falsifiable. These two groups may be the same group, maybe the same group of people, just pre-post, before an intervention and after an intervention. But still two measures of something being compared. The last thing here about designing a hypothesis, hypotheses need to be stated in the affirmative, they need to be positive. You've got to predict the presence of a relationship between or among variables rather than the absence of a relationship. And this is partly because of the statistical logic behind hypothesis testing, which we'll look at momentarily, and partly because of kind of a historical cultural tendency to adopt the innocent until proven guilty approach to science. But there's this assumption that variables are not related. And no relationship is thought to exist until it has empirical support showing that the relationship does exist. So if someone told you 70 years ago that they thought smoking caused cancer, if you were a good scientist, you'd say, well, that's an empirical question. Let's investigate to see if this is true. So if you start from the position of assuming a relationship does not exist, then it doesn't make sense to do a study looking to confirm what you already believe to be true. Now, sometimes evidence will build that a relationship between two variables exists. And so, okay, now we think a relationship exists because there's evidence. And if you believe that people have changed, society has changed in some fundamental way that would lead this relationship not to be true anymore, then you might pursue that field of research. But you need to conduct research examining the change. So for example, think about what would happen if smoking used to cause cancer, but now it doesn't because people evolved. Well, then, if that happened, then logically, the rates of lung cancer among smokers would have decreased over time. and I can look at that change. That's something happening, not just an absence of relationship. So you're predicting something, not nothing. Okay, now let's look at excuse me. Let's look at how we test these hypotheses. Okay, so the major approach to testing hypotheses when it comes to statistical testing is NHST, Null Hypothesis Significance Testing. So start talking about the null hypothesis. It's generally the opposite of what you hope to find. So again, we try to form hypotheses in the affirmative as a positive. So the null hypothesis is a hypothesis of no relationship or no effect. So if we look at kind of statistical notation for the null, this is looking at a cause-effect relationship, group differences, comparing two groups. The null hypothesis is that mu1 is equal to mu2. So the average of whatever, average depression score, average amount eaten in an hour in a population, whatever, in one population is equal to that of another population. And usually one population will be your control and the other will be your treatment group. Right? So you want those two means to be different. But the null is that they're not different. And notice the notation is mu, not x bar. So the null hypothesis, hypothesis testing is about populations. We make these hypotheses about populations, but we test samples, and all our statistics look at statistics, not parameters. They look at measures of samples to estimate things in a population. So we have hypotheses about populations, and we test samples, and then our stats kick in to help us estimate the probability that what we found in our samples is going to be representative of what we would have looked for in the whole population. Okay. So the null hypothesis, we see that. So the alternative hypothesis then is generally what you hope to find, and so it's that a relationship or effect is present or presented, if you like the typo. So again, kind of notation, h sub 1 or h sub a, mu1 is not equal to mu2. Or it could have been mu1 is greater than mu2, or mu1 is less than mu2. But, however, that it needs to be exhaustive when paired with the null. So the null and the alternative together need to account for all the possible outcomes. So we couldn't have had, the null is they're not equal, and the alternative is mu1 is greater than mu2, because that wouldn't account for the times when mu1 is less than mu2. So if you're going to use greater than, it has to be probably your alternative would be, for example, mu1 is greater than mu2. So the null would be mu1 is less than or equal to mu2. So it accounts for, again, all the possibilities. And again, these are just for cause-effect, looking at two groups. If it were correlational stuff, we'd be talking about the correlation is 0, so rho equals 0. If there's no relation between two variables, then the correlation statistic would be 0. Important thing to note here before we get too far off, though, is that when looking at comparing these means, if one mean was 1,000,000.1 and the other mean was 1,000,000.2 in the population, then the null hypothesis would be false. So yay, you're right. You found what you're looking for. So it is that really big a deal. We'll talk about again in a little bit. Okay, so why do we test the null and not the alternative? Why don't we have alternative hypothesis significance testing? Why is it null hypothesis significance testing? Well, it really has to do with the math, the kind of probability statistics behind all this. To remember, the null hypothesis is about populations. And when looking at cause-effect studies, we're talking about two or more groups. And for simplicity's sake, we'll just talk about two groups for now. Think about a treatment group and a control group. When the null hypothesis is true, right, so mu1 is equal to mu2, there's a clearly discernible mathematical relationship between the means. Their difference is equal to 0. Right? Mu1 minus mu2 is 0. Mu2 minus mu1 is 0. That's pretty straightforward. When the alternative hypothesis is true, the difference between the two means could take on an infinite number of values. which as we'll see in a minute would be harder to use our stats with. But when we look, okay, if the null is true, the difference in two means is 0, well, we can do some pretty cool stuff with that. So based on something called the central limit theorem, which we won't go to in depth now, hopefully you cover this in your statistics class, but we know that if the null is true, then the typical difference between our two samples, treatment and control, will be 0, right? mu1 minus mu2 0. And so we can think of the kind of this population of differences where, sometimes the difference will be greater than 0, sometimes it will be less than 0, depending on, which of our samples is the higher score. And then we can actually calculate the probability of a particular difference between two sample means that would be observed if the null was true. And note here, I keep saying if the null is true, because this is a conditional probability. It's the probability of finding a difference between means, sample means, when a particular condition is met. In this case, the null is true, which down the road we'll talk about why it's important that it's a conditional probability. But right now I just kind of want to point it out for you. So if we kind of imagine the differences between two sample means are normally distributed, which is one of the tenets of the central limit theorem, which if you do some kind of play with numbers, you'll find that that's true even if the samples that you're using aren't normally distributed themselves. The differences between those things, if you get enough samples of enough populations, they'll be normally distributed. And if the null is true, they would vary around 0, right? So some more than 0, some less than 0, most of them 0 or close to it. And like I said, if this is a normal curve, then we can apply what we know about the normal curve to figure out the probability of getting a certain difference. So when we find a difference between sample means that's very large, positively or negatively, so out to the right or the left of this curve, it has a low probability of occurring when the null is true. When that probability gets low enough, say around 5%, then we reject the null hypothesis. And if you reject the null, then you've supported the alternative hypothesis, because that's the only other thing that it could possibly be. Okay. So again, null hypothesis statistical testing, significance testing, is all about assuming the null were true. How rare would it be to find this effect that we found? And if it's really rare, then we think the null is false. And if we think the null is false, then we think the hypothesis is probably right, which is very roundabout logic and criticized by some, which we'll see in a minute. Okay. So you make a decision regarding the null, which you can either reject the null. Right? When we reject the null, whenever we get an effect, when we get a difference between sample means, or we get a correlation that's big enough different from 0, to say that, wow, it would be really rare to get that if the null were true. So here you're saying, I'm pretty confident, given the probabilities here, I'm confident that the null is not true, and that these two groups are not equal. These two samples aren't from the same population. So I'm going to reject the null. Excuse me. Or, alternatively, I may fail to reject the null. So if I'm not confident enough that the null isn't true, so maybe I found a difference between several means, but it wasn't 0, it was 0.1, or it was maybe even 10, but 10 wasn't big enough. So it's not big enough a difference, not a big enough effect for me to be confident that the null is not true, so I fail to reject the null. Now note here that I don't say I accept the null. Right? Because just because we didn't find a difference doesn't mean one's not there. And again, this has to do with this kind of level of confidence thing. And sometimes we'll set, we want to be 95% sure. Again, there's where that 5% comes in. If I'm 95% sure that these two populations are different, well, what if I was just 94% confident? So, something was pretty rare, but it happens 6% of the time when the null is true, and that's not enough for me to reject the null. Well, that 6%, that 5%, are they really that different that you're willing to say, okay, I now fully believe that the null is true, and these things are absolutely not different? Probably not, and that's why we use this language. It's not just semantics. There is kind of reasons. There are reasons behind this, the way we state things, and they do have meaning. Okay, so you either reject the null or you fail to reject the null. And again, generally, you're hoping to reject the null. You want to say, no, these two samples are not from the same population. They are different. My treatment did have an effect. The treatment group was different from the control group. The people were different after they took the pill than before they took the pill. Whatever it is you're looking at, you want to say that they're different, which means rejecting the null. So when you reject the null, that then has implications for the alternative hypothesis. And again, you're not testing the alternative, you're testing the null, and then it has implications for the alternative. So if you reject the null hypothesis, then the alternative hypothesis is supported, and the two groups appear to be different. Right? And again, we can't be sure that they're different because we might have made an error, which we'll see in a minute, but we say we support the alternative. So again, we don't accept the alternative. We all use very tentative language in talking about these things, other than rejecting the null. But we support the alternative hypothesis and we think, okay, the two groups are different, the treatment had effect, whatever, some good things. If we had failed to reject the null, then our alternative hypothesis was not supported. The two groups might not be different. There was just insufficient evidence to conclude they were different. It's kind of like, they're not innocent, but they're not guilty either. So when you find somebody not guilty, but you still think they're guilty, well, you couldn't find them guilty. You had enough evidence to prosecute, but I'm still thinking maybe my hypothesis was right, and I just didn't have enough power or whatever. So those are kind of the impact. That's the impact they can have on the alternative hypothesis. Okay. So you make your decision, and there are outcomes, right? And the outcome depends on what you decide and what is really true. And you can obviously know what you decide. We have power over that. What you cannot know is what's really true. You cannot know whether the null is really true or whether the null was false. But we have ways of estimating the probability of errors if the null is true or if the null is false, which we'll see in a second. So if we reject the null, but the null was true, so I said rejecting the null, there's not a difference, right? That's double negative. So there is a difference in two groups. They came from different populations. I disagree that they came from the same population. I'm rejecting the null. My treatment worked, but in fact, the treatment didn't work. The two groups are from the same population. The depressed group that got treated and the depressed group that didn't get treated are exactly the same, have the same scores. Then you've made an error, and you've made a type 1 error. So type 1 error is when you reject the null when in fact the null was true. So you said the groups differed when they didn't really in the population. So they may have looked like that in your sample, but the population, if you look at enough people, you would have found, oh, that wasn't true. You just kind of have something squirrely going on in your study. So if you conclude there's an effect when there's not an effect, again, that's a type 1 error. And that's one that we try to protect against, as we'll talk about later. We'll talk about data analyses by setting the alpha level at a certain level. So what if you reject the null and the null is false? So same decision, different reality. Well, obviously, if you don't make an error, the opposite thing is you've made a correct decision. So you reject the null is false. So you said your treatment worked, and in fact, in real life, it does work. If you look at all the population of all the people who could ever be treated and untreated, you would find this difference. It would be repeatable. And that would be a nice thing. So what about if you fail to reject and the null is true? So you say, oh, my treatment didn't work, and the null is true. Well, if the null is true, the treatment didn't work either, so yeah, you're right. And that's unfortunate, but at least you haven't made an error. So you have that going for you. And then the last thing would obviously be an error. If you fail to reject and the null is false, now you committed a type 2 error. So a type 2 error is when you say the groups did not differ. So in your samples, the groups look like they didn't differ. There's no relationship, no effect. But in the population, there really is one. And you missed it. So you concluded there's not enough evidence to work, but it really did. And the type 2 error is one that happens when you have insufficient power, which again we'll talk about in the future. And historically, type 1 errors have gotten much more attention than type 2 errors, but that's changed in the past 10 years, and probably for a good reason. And depending on your research question, kind of what's at stake, type 1 versus type 2 error one or the other becomes maybe more important. So it's not always, oh, this one's always more important. Depends on the situation. Okay, so these are the outcomes of decisions, and again, we'll come back and we'll look at these more closely when we talk about data analysis. But just kind of want to give you a preview of what we're talking about in the future, so it all kind of is connected when we get there. So we spent some time talking about null hypothesis statistical testing, and you've probably picked out already that it may not be the best thing since sliced bread. In fact, there's been a kind of growing waves of criticism of null hypothesis statistical testing in the past, I'd say 20 years, going back to the things that Cohen did. And for good reason. And we'll talk about some of the things that are wrong with it, and then some of the alternatives to relying solely on NHST. For one thing, the null is almost always false. Because remember, generally we state the null being that these two groups are not different, they're exactly equal. And if you get enough people, surveyed, you have enough power, you're almost always going to find that they actually are different, even if they're only slightly different. We talk about 1,000,000.1 versus 1,000,000.2. If that's the case, the null is false. It doesn't really matter because there's probably no meaningful difference between two variables when one's at 1,000,000.1 and one's at 1,000,000.2. I can't think of any good examples where that kind of scale of difference would matter. So realistically, the null is almost always false, and so it's kind of a paper tiger, a straw man that you're setting up to test. Excuse me. On a related note, it's also it gets confused for some people between whether or not they think of this as being a test of the hypothesis, and it's a statistical test that's used to evaluate hypothesis in a given study. But the results of this statistical test aren't the sole piece of evidence to determine whether or not a hypothesis is valid or invalid. No, it's a piece of evidence, but it's not the only piece of evidence, and for a variety of reasons. One, because of the way that the tests are run. Another, because there could be plenty of flaws in the study or unique things about the sample that don't provide really an optimum test of the hypothesis. So again, this is just a test of some data that's been used to estimate kind of a test of hypothesis, but it's not a direct test of hypothesis. This is just one of the better things we have. We'll talk in a minute about some newer things. Also, p-values. You always hear about p equals 0.05, p equals 0.01. P-values are often mistakenly interpreted as indicating a level of significance. These things, it was a significant effect at 0.05, but the other one was significant at 0.001, so it was clearly a stronger effect. Absolutely not. Makes no sense whatsoever. Null hypothesis statistical testing is yes/no. With p-values, there's no degree of effect. There's some other ways to look at degree of effect, but the p-value has nothing to do with that. That's too heavily influenced by sample size and some other measures of variability. So don't ever tell people, at a really significant finding, it was 0.0001. That doesn't matter. Related to that, NHST doesn't provide a test of clinical significance. So even if something is statistically significant, so two groups are statistically significantly different, but to conclude from that a treatment worked, that might be problematic. If you're trying to treat depression, to people that are kind of at risk for suicide, and you get a bunch of people and you have a treatment group and a control group, and you run a study and you find that the treatment group scored reliably 2 points lower on the depression scale than the control group, and you say your treatment worked, and yet if you look at other measures, you see, okay, well, they scored lower on the depression scale, but there's no difference between the two groups in numbers of completed suicides. There's no difference in number of missed days work. There's no difference in marital problems reported. If there's no real differences between these groups, other than some kind of slight numerical difference on a scale, then you can't really say it worked clinically. It led to an observable difference on a measure, but that's not the same thing as helping people and working. So there are these criticisms of NHST, and so you might have been asking yourself, hopefully you're asking yourself, what are the alternatives? And again, these are alternatives in terms of, for most people, it's NHST plus these other things. We're not going to ever probably, in the near future, abandon null hypothesis statistical testing just because there's so much accumulated evidence built up in all different areas, at least in our science, using this approach. But not relying on it as the sole kind of method of evaluating hypotheses is definitely a big movement in the field. So the two things we're looking at now, one being effect sizes, and there are different ways to calculate effect sizes, but generally effect sizes it's a statistical approach of trying to look at some sort of standardized measure of how different two groups are or how strong a relationship is in a kind of a standardized way, so you can look across studies and compare, okay, in this study then effect size of 0.1, in this study an effect size of 0.2, this treatment had a bigger effect, and so you can compare across studies. It's kind of the idea behind these effect sizes. And the other idea that I think is maybe gaining more ground lately is going back to kind of an older thing you probably learned in your first stat class, is the use of confidence intervals. So creating a confidence interval around a mean, around two means, and then looking at the degree to which those confidence intervals overlap. If they don't overlap, then we think, okay, those things seem to be pretty different. And if they do overlap, we're not as sure that those things are meaningfully different. And that kind of gets at, okay, we found a mean here at 10 and a mean here at 8, but how variable were the scores in those things? If they're very variable, and there's lots of overlap in the confidence intervals, then the 8 and the 10 may not be meaningfully different. But if all the numbers are really tightly packed around that 10 and really tightly packed around that 8, and you've got really small confidence intervals, then visually you can see those seem to be reliably different outcomes for those two groups. And an even newer thing that people are moving toward now possibly is constructing confidence intervals around effect sizes. So really going all out with this kind of alternative approach. But again, not abandoning NHST. So also we talked about, you don't think, oh crap, it's all wasted. It's using null hypothesis statistical testing and these other things to help people understand exactly what our results mean. Which again, when we talk about data analysis, we'll get into this in a bit more detail. Okay, so to sum things up, two main things to talk about. One, writing good hypotheses, which the key is having them be logical, trying to use that kind of if-then format. If A, then B. The way to test it is, well, if not B, then not A, and does that make sense? And then if you're going to move science forward, try to think of hypotheses that will evaluate and inform theories, inform our theoretical knowledge. That way we're kind of dealing with these conceptual frameworks, testing them, reevaluating them, refining them, so that we have an overall better understanding of how things work and be able to make predictions about people and maybe design better treatments. And then the other thing we talked about, obviously, was NHST, which for some of you it may seem a little counterintuitive that we're even though we think one thing's going to happen, we say, okay, well, what if the other thing happened? What if the opposite of what I want to happen? What if there was no effect? And then we look for what's the probability of finding what we found if that were not true. And if it's a lot, then I say, okay, I'm wrong about it not being true, so it is true, which is very confusing. But most people just point and click on SPSS and don't bother with it. But hopefully you'll try to spend some time thinking about it and trying to wrap your head around this kind of cumbersome way of testing statistical hypotheses. But as you do that, keep in mind that it's not sufficient when used alone. But I don't want you to accept, oh, Dr. Fail said it's not sufficient. I want you to understand it so you can decide whether or not you think, oh yeah, I agree, it's not sufficient when used alone. I want to be sure and learn how to calculate effect sizes and confidence intervals, or I thought about it in null hypothesis statistical testing, significance testing makes perfect sense to me, and I think it is an appropriate way. And then you make a decision about what you think is the best way to analyze your data. All right, hopefully some of that makes sense, and I'll talk to you later.